All right. All right, we're live. Hey, Richard. Hey, Ian.
Hey there.
And hello, everybody popping in. Welcome to Coiled's November webinar, Higher Performance Python for Data Science. I'm Christiana from the Coiled team, and I'm here with our special guest, Ian Ozsvald, Principal Data Scientist at Mor Consulting, and our host, Richard Pelgrim, who's our very own data science evangelist here at Coiled. How's it going?
Very good, very good. I mean, we say
Great.
principal data scientist at Mor Consulting, only data scientist at Mor Consulting as well, because I run my own
Got
company.
it.
So
The one and
principal,
only.
chief, T-boy, the whole thing.
Every hat is worn.
Every
I
hat.
love it.
Yeah.
Cool. Well, for everybody joining us, thanks so much for being here. We would love if you would introduce yourself in the chat. Tell us where you're tuning in from, and we're going to kick off the convo today just with a warm-up icebreaker. And that question we'll pose to Richard and Ian, but feel free throw your answer into the chat. And that question is, what was your first use of Python for analytics? So Ian or Richard?
So I'm happy to go first with this because it's still a strong memory, and it was 2003. So what's that, 18 years ago. So I was working at the time in an AI startup in London, a French company with a Brighton, south coast of the UK office, Mathématiques Appliquées SA, so MASA. Which is still going in France, providing solutions to various aspects of business and government in France. I was with them for 5 years, and I was the first UK employee, and I was super down on C++. Everything was C++ because I really cared about my high performance computing. The subject of this session. Really cared about the high performance computing, and C++ was where it was at. Super expressive and very fast, and you can exploit yourself all the way down to the register level. And we were several years in, big C++ stack, solving traveling salesman-like problems with an evolutionary computing framework using genetic algorithms, the wave of the future, the thing that would define AI for the decades to come, which of course didn't turn out to be true, but hey, it's an interesting technology, made some really cool solutions out of it. And then one day, one of my French colleagues sent me a work request and said, hey, Ian, we need you to do this, some work on some Python, which you may not have come across before. We need you to write a SAX parser, S-A-X, so it's an HTML markup language equivalent, to process these web documents that we've got. And I sat back horrified. Why do you want me to use this ridiculous interpreted language? There's barely any books on it. I go down to Borders and I can find a couple of books, but they're all just kind of weird, and there's strange snake thing going on. It's not a serious programming language. Why would I go and use this silly language? And it's interpreted. It's slow. What am I going to do with this? And I was all right, fine. They've given me the sample code. I'll just read it. I'll read some tutorials online. Found a couple of this is all pre-Google, of course. Found a couple of examples online. Began to do it, and then. I think in the space of a day or so, I had a working solution. And then I sat back and thought, oh, as a senior data scientist for 5 years, running a team in this company with C++, I couldn't have created this solution in the time that I did, but I made it using Python, learning as I went, and it works. But, oh, I'm much more expressive and powerful than I was before by using this new language. Maybe I should pay attention to this silly interpreted language. And then I never looked backwards. So that's my onboarding experience in Python.
It's an awesome origin story. Thank you for sharing that. Richard?
Yeah, my origin story doesn't quite go back that far. I started writing Python, I think about a year and a half ago, when I was starting to make a career switch into data science. And my first real project was I grew up in the Middle East, and I had heard kind of I grew up in Lebanon, and there was the war in Syria was going on, and I'd heard some rumors, people kind of guessing some theories about climate change being an important contributing factor to the political instability that was going on there. And I wasn't reading much about it, and I thought, hey, maybe I can use this new skill to see if there's anything to that. So I ended up looking at a lot of combining two data sets, one with climate data and one with armed conflict data, and trying to see if there were any patterns that emerged from that. Pretty big topic to take on as my first Python project, and
totally
no conclusive no conclusive findings, as with many data science projects. But it was a great way to really enjoyed. I think, yeah, Ian, what you said, being able to go from kind of an idea to executing something very, very quickly in the space of a few weeks. So
Totally.
Yeah, no, it's totally true. And when I've given some keynotes in the past, one of the point that I've made is that, hey, everyone in the room, you know, you're here, you're in a keynote, we're talking about Python and data science, and that's all lovely and great. But don't forget that compared to your population, you are the 1%. You're the fraction of a 1%. You're the people who can turn that raw data you can get from the government website into something that's interpretable. And otherwise, this data is all hidden away. And then I've had people come to me afterwards and go, you know, I'm struggling with my career. I'm not quite sure where I am. And it never occurred to me that I am that translator who can take that data and ask some questions or collaborate with someone who's asking questions and give answers that otherwise most people would never have access to. And actually, that's incredibly empowering. And that's one of the reasons why I like Python. We get our answers quickly, and it's powerful, flexible, and expressible. It does lead to problems. Too many people come into the language thinking, great, I'll just do this little thing. And then, hey, how do I scale up to this slightly bigger data set that happens to be huge? And of course, Richard, we're going to touch on that later on. But those are fun problems to have. Hey, you're on the journey at that point.
Absolutely. Well, I'm already excited just from the warm up. I'm excited for the next hour or so with Richard and Ian. So before I pass it over, I'm just going to read out each of their bios. But if you're just joining us, please introduce yourself in the chat. Tell us where you're tuning in from. You can answer that icebreaker question we just had. And then I'll pass it over to Richard and Ian. So first, Richard. Richard is a data scientist and technical communicator with a background in geography, anthropology, and the arts. He enjoys forging creative connections across disciplines and is passionate about contributing to a more equitable and sustainable planet. And he is our data science evangelist here at Coiled. And then Ian, our guest today. Ian Ozsvald is a chief data scientist and coach. He's helped co-organize the annual PyData London conference with 700 plus attendees and the associated 11,000 member monthly meetup. He runs the established Mor Consulting data science consultancy in London, gives conference talks internationally, and is the author of the best-selling O'Reilly book, High Performance Python, 2nd edition. He has 19 years of experience as a senior data science leader, trainer, and team coach. For fun, he's walked by his high-energy Springer Spaniel, surfs the Cornish coast, and drinks fine coffee. So that's a little bit about Richard and Ian. I'm going to pass it over to you. Everybody feel encouraged to answer questions in the chat. Make sure you set your question sending to everyone so we can all see them. So yeah, let's take it away. Thanks, everyone.
Thanks a lot, Cristiano. And great to be here. Yeah, great to be here, Ian. Looking forward to this presentation. Do you want to go ahead and share your slides, and then we can
absolutely. So I'll do a screen share. And everyone, please, in the chat, do share your origin story as well. And if you can hear noise in the background, Richard, you might have to tell me. My Springer Spaniel is trying to bury something behind me at the moment. So if she's becoming annoying, tell me, and I'll mute myself temporarily. Sure. I'm not quite sure what she's burying, and I wish she wouldn't, but I'm sure it's terribly
for everyone watching, we really would like for this to be a very conversational session. So feel free to jump in with questions. We'll try to pull them in as they come up, and yeah, let's dig into it.
Okay, so you can see my screen, Richard. Is that right?
Correct.
Things look good. Right, perfect. And can you hear the dog in the background?
Barely.
Yeah, okay. I think she's found the Christmas paper pile and she's burying something in there, which is not ideal, but hey, it is what it is. Right, so hello everyone. So my name is Ian Ozsvald, and we'll be talking about high performance Python for data science in this session. As Richard mentioned, I'm dead keen that we turn this into a bit more of a conversational session. I've been giving conference talks via Zoom for all of the pandemic. I'm a tiny bit bored now of hiding behind a screen and then lecturing away and not having good conversation. So there's a couple of slides throughout the talk where I ask a question. I'd like you to start thinking about it in the audience. Please contribute your answer via the chat window. Remember, as Cristiano says, to address to everyone. I've already sent a DM by mistake because I got it wrong. So send your reply to everyone. Richard and I will be talking. I'm hoping that Richard will come up with some points during this, and we'll have a bit of back and forth. And if you ask questions, then Richard will be monitoring, and he might interrupt me and bring up the question. And then once we get to the end of the talk in 30 minutes or so, we'll open up some Q&A. And a particular point of focus for you on this call will be the Dask onboarding experience, because Richard handles that. And so I know a little bit about that, but Richard knows quite a lot, and he's got a tiny demo for us. So if you've got questions about moving from Pandas to Dask as a particular bit of the high performance journey, Richard is the right person to ask, and we should utilize that for the Q&A later on. So do please get thinking about it. Okay, so what are we going to be talking about today? So for this slide component, we'll be looking at a little briefing on profiling in Python, a forgotten bit of the landscape, and compiling in Pandas, and then scaling up, looking for bottlenecks to help you develop faster, and then having some Q&A right at the end. Yeah, questions, please do post these in, and we'll do the live Q&A later on. Oh, and I see good origin stories coming through on the chat. That's brilliant. Keep those origin stories coming, please. So who am I? I call myself an interim chief data scientist. So I don't work as a permanent employee anywhere. I work in a number of organizations. I consult currently in financial services, particularly insurance at the moment, going in to help existing data science teams figure out their strategy. We're developing some things, but we're not shipping enough. It's not working enough for our clients. What do we do? And so, well, I've been doing this for 20 odd years. I can help you figure out what it is that isn't working and how we turn it into something that is working. So how we get data science products shipped. I still write code. I used to write a lot of code, used to do a lot of intellectual property solutions. But I really like now, rather than just delivering one thing, helping a team to deliver lots of things, because I get to learn lots more that way. And I love learning new stuff all the time. I also give, so along with the team coaching, I run public courses. One of them is on higher performance Python, and then my book is there. It's this book here, and it's reassuringly thick. It looks like a proper book. The first edition was a bit thinner, but this one's a decent size. There's a good amount of knowledge in there. I gave my first high performance tutorial Euro SciPy, I don't know, 2012 or something, so sort of 8-10 years ago, and then I've been talking about it every year since then, and iterating and evolving the material. That turned into the first edition of the book, and then the second. 8 years ago, with a couple of colleagues, we started the PyData London meetup, so part of the 180 public groups around the world running PyData open meetups. And then I'm one of the co-founders of the PyData London conference, which pre-pandemic would raise a lot of money for NumFocus and the PyData ecosystem, and the 100 or so projects that are covered inside NumFocus, tools like Jupyter, Pandas, NumPy, SciPy, and a whole bunch more, which are funded in part via NumFocus, which benefit all of you and your careers. And many people don't realize that. So it's important to look where the money comes from to support these open source projects, and then get involved in the PyData scene. And then you can help to grow the ecosystem. So here for this talk, I'll be sharing some bits from my book and my training courses, because I'm always updating my material. I love talking about it. I love to find out what works and what helps. So tell me what works and what helps for you. So where are we in the ecosystem now? So Pandas is the default. It's the main tool that we all use. I'll introduce a couple of Pandas alternatives right in one of the last slides. But pretty much all of us, if we're doing analytics, will be using Pandas. But there's lots of warts and rough edges there. We'll touch on a couple of those later on. The fact that it uses high amounts of RAM can be really frustrating. I've got 32 gig in my laptop, and with a 10 gigabyte data set, I can easily run out of RAM by doing a large manipulation that I wouldn't think takes all the RAM in my laptop, but it does. So that can lead you to scaling problems. But hey, we've got some solutions for that, including Dask, that Richard will talk on about a bit later on. One of the ways to get past some of these issues is to think about profiling. And so I've got some slides introducing a couple of common profiling tools. And so few people know about profiling, and then they forget to go and profile their code. It's one of the easiest ways to get a win. And then certainly in the industry, there's always a bit of pushback. Hacker News tends to have some long, stressy arguments at times. Python's rubbish. It's ridiculous now. It's single-threaded. You can't scale it. The global interpreter lock is a bad idea and should be ditched. It's all interpreted. interpreted, it's too slow, go and use a proper programming language. And that's kind of ridiculous. And I always try to just gently dispel some of those positions. So where are we now with Python? Well, if you follow the TOB language index, so it's an index which looks at the number of questions asked, the number of books published, the number of job postings that are out there, and it compiles it all down into a league table for programming language popularity. It used to be the case that Python was like number 20 and then number 10. And then a few months ago, it became number 1. So all of a sudden, we've got the best language on the planet, at least by the TOB index's methodology for ranking the number of people using it, being employed, buying it, writing about it, and the like. It doesn't matter that it's number 1, number 2, whatever. It matters that it's got a lot of mind share. A lot of people are using it. So they're using it for a good reason. And one of the reasons is it's kind of the second best at everything. So it's not single best at one thing. Many languages try to specialize in one good thing. Python's just a really good glue language that lets us do lots of things pretty well. Not necessarily optimally, but pretty well. And that means it's really hard to displace it because it gets glued into all of the places out there. So if you're focusing on Pandas for your career, well, you're in good company, and you're going to be in good company for decades to come. What about the alternatives in the Python ecosystem? If you go searching around, you'll find that there's lots of other Python tools out there, and you may think, hey, that must be better and faster over there. Maybe I should go in that direction. So on the left-hand side is the logo you know and love. That's the standard CPython interpreter. That's when you type python.exe in Windows, or you just run Python in Linux and Mac, you get CPython, the standard Python. That's the thing that we all know and love. In the middle, I've got PyPy. That's a just-in-time compiler around Python, written in a restricted subset of Python. And then it gives us, they aim for a 4 to 10x speed up on regular Python code. It's a really, really interesting project, been going for a couple of decades now, I think. Big European Union funded project. And it's a really impressive piece of machinery. The one downside is that it doesn't integrate very well with the NumPy and Pandas ecosystem. So for quant work, we don't seem to use it very much because it doesn't integrate well. It actually works, but it poses some really big speed overhead, so it's not so interesting, which is unfortunate because otherwise it would give us some nice speed ups. There's Piston, which I think came from Dropbox, and I don't know much about it. I was looking at it recently. Seems to be I think a commercially supported entity. They promise a 30% speed up and NumPy and Pandas compatibility. Looks super interesting. There's a couple of others. There's also Jython, Python in Java, Brython, Python in JavaScript, IronPython, Python in .NET, the Nuitka compiler. And so all of these things give you sort of different angles on the use of Python. But, do you need to use them? Well, it depends. If you're not in those other languages, probably not. And then Cython and Numba, Cython being a C-based compiler framework, which is used heavily in our quant world. So it's baked into Pandas and scikit-learn, for example, wrapping up all of the underlying libraries in a fast C or Fortran wrapping compiler framework. Super mature technology. It's been around for decades. And Numba, which I'll be introducing later on, just-in-time compiler, just for our quant work. It does a bit of pure Python as well. So it does a bit of what PyPy does, but aimed at our use case. So super useful to us. And then some specialized compiler options like Pythran. So you've got a lot of options. Which one would you want to use? Well, the answer is going to be stick with what we know, CPython. I'll mention that in a moment. One of the reasons is there's an interesting new proposal that's just started in the last 6 months or so by a colleague of mine, Mark Shannon in the UK. He proposed a project. He's been talking about this for a couple of years, and he put forward a proposal, I don't know, 6 months, a year ago, saying that, look, hey, if a big pile of money was put up, so $2 million is the number he quoted, I see a bunch of milestones that can be achieved, which will bring in a whole bunch of optimizations, including a just-in-time compiler, into the regular CPython project. It won't break backwards compatibility, and so it'll work with all the tools that we use, including our ecosystem's worth of tools, and it will give us, hopefully, a 5x speed up in some number of years, but a near-term goal. He talked about trying to push this as a community thing, raise the money. That didn't work out. But then Microsoft stepped up and employed Mark Guido, the language creator, and I think a third person on a project to push this forward. So this is pretty early stages. A bunch of cleanup work is happening at the moment. One of the goals is that by Python 3.11, which will be next October's release, there will be a just-in-time compiler baked into the core of Python, and that will be one of the next stages in giving us another improvement in speed. So it may not impact our NumPy and our Pandas work and our Dask scaling, but it will impact all of the other use of Python around this, all of the data loading, data munging, all of that stuff, which is super interesting because all of a sudden it looks a little bit more like .NET and Java and JavaScript with their just-in-time built-in compilers. So the short story is, hey, stick with CPython. You don't have to go off the beaten track. Just stick with the thing that we know. It's compatible with all of our tools and it makes our life easy. The other thing to think about is when you're learning new libraries, well, which libraries are foundational, which ones make our life easy and are used by everyone and will be around for a long time. And the solution there is it's the libraries like NumPy and Pandas and scikit-learn. So NumPy is the numeric Python framework. It gives us our vector and array-based computation. Pandas at the beginning was a thin wrapper around NumPy that added indexes and some convenience functions and has grown into a richer project. And scikit-learn always was and still is based heavily on NumPy, and then gives us machine learning algorithms built on top of NumPy. But now even scikit-learn is an interface layer to other tools like visualizers, and so TensorFlow has to expose a scikit-learn compatible API, which means that you could use it in the visualizers that visualize scikit-learn estimators. So scikit-learn becomes one of those standards in the ecosystem that other tools build upon, and that stands upon, or next to Pandas and stands upon NumPy shoulders, standing upon pure Python shoulders. So if you're looking for a long-term career doing high performance analytics work in the Python ecosystem, these are just the tools that you want under your belt. There are other interesting, Richard, please.
Yeah, no, I was just wondering, in your previous slide, this grand plan that's coming up, did I understand correctly that it won't actually improve or speed up NumPy and Pandas code?
So as I understand it, it's only for improving the internals of CPython, and much of NumPy and Pandas, it will be precompiled C and Fortran libraries that are wrapped up inside some Python. So it may have knock-on benefits, but the real goal is not to speed up that precompiled code, but just to remove some of the need to have precompiled code in the first place. Sure. If it turns out you don't have to write in a second or third language like C or Fortran, which you wrap up with Python into a Python presentation layer, which you can then use easily in Python, but you could just write the algorithm in pure Python and it goes at the same speed or similar speed. Hey, your maintenance load comes down. Sure. And your developer applicability widens because you don't need someone who's an expert in two languages. You just need someone who's good at the one pure Python language. Yeah. So I suspect it will have knock-on benefits, but not a direct performance.
And do you see it leading to the development of sort of NumPy or Pandas alternatives, since those things don't need to be written in different languages anymore then?
So that's quite feasible. There is, for example, an array interface in pure Python, which gives you a NumPy-like container, a homogeneous typed vector container, and I think a matrix as well, and some other operations there. And that doesn't go any faster than NumPy, and often it goes slower than NumPy, but there's reasons why that could go faster under this paradigm, or you could build another tool, of course. So yes, that's possible, but also then you've then got to dislodge NumPy. And if you're competing with NumPy, then you're competing also with scikit-learn and Pandas and having to dislodge that ecosystem to get users to your new ecosystem. So there's there's a community split problem there, I guess. Sure. But I think it just means it's easier for anyone to write fast, computational, interesting libraries. And as you say, you're sticking with pure Python. So it's going to increase experimentation by people, and who knows what comes out of that experimentation. Sure. Okay, so yeah, to final point there, so if we've got other libraries like Polars that I'll mention later on and Vaex as Pandas data frame competitors, they're super interesting. You should definitely experiment with them. But it becomes increasingly hard to displace them because Pandas becomes a foundational layer for better or worse, and there's a whole bunch of worse about Pandas, unfortunately, due to its heavily evolved design. There's lots of warts and weird edge cases in there, but it's become foundational, so it's just the tool that everybody uses. So definitely experiment with these things, but for a good, happy, performant career, stick to the main path and keep improving your skills there. So question for the audience. I'm going to talk about profiling for the next couple of slides. Have a quick think about how you currently profile. Do you profile? I hope you do. Many people don't. Can you share a couple of your own tips from profiling? And if you want to share, just put it into the chat window, please. Particularly, I'm only going to cover a couple of libraries. If you've got other tools that you like to cover, please post those in the chat. And when we move on to the next section, you can, of course, still make points about profiling. It'll be really good to compile some of that knowledge to the chat right now. And so, Richard, question for you. Do you profile your Python code? Have you, what have you found to be useful there?
Yeah, good question. So, I've been writing Python code for about 1.5 years, and I think I really started profiling Python code when I started using Dask, because Dask makes it so easy. So we'll jump into that later in this presentation. But with the Dask dashboard, it's just really easy access to see what's going on with your computations. And I found that the fact that visualization was so accessible made you think, okay, there must be ways to optimize this. And so that's really where I've done most of my profiling. The other kind of very basic profiler is just the time magic in Jupyter Notebooks. If I'm kind of curious about how long something's taking and I want it to speed up. Yeah.
Perfect, right. And so I see in the chat, Jesper, you mentioned cProfile and SnakeViz, super sensible foundational profiling tools. And Dylan, you've mentioned pProfile. I've not used pProfile, so I haven't got an opinion. If you wanted to share a sentence on why, both of you, on why you use those tools. Oh, and Guraj and Sami, a couple of notes on why you use them to educate others. That would be super useful. I'd be reading that very happily. Oh, and print statements, printing time. Yeah. Totally, print statements rule, one of the best debug aids out there. I don't care what anyone says, I put print statements everywhere because it makes life easy. So yes, please put a couple of notes on your use cases for these tools to help everyone understand why they might want to look at these. So when I teach and in the book, and this is just based on historic wins, I start with Line Profiler. For any numeric work, I go straight for Line Profiler. It's a pretty popular tool. I did a bit of estimating based on download stats, and I reckon there's 2 million downloads a year. But whenever I teach, almost everyone has never heard of it. And whenever I talk about it, people haven't heard of it. Line Profiler is brilliant. You should give it a go. It's a deterministic line-by-line profiler. Deterministic means it times every line of code that's being executed. So you don't miss anything. There's no sampling in there, which imposes an overhead, but it does mean that we get really fine-grained detail on how long each line of code takes. It can only profile Python code. So if you compile something, it can tell you how long the call to the compiled function took, but it can't tell you how long the lines took in the compiled function, because of course the compiled function is no longer Python, it's become machine code or LLVM or something else. And so we can't see what the Python equivalent is in there. So we lose some introspection ability. But for all of our regular Python, and if you're using NumPy, it's kind of amazing because you can see exactly when your NumPy is going too slow, which is great. It works in the notebook, and it works on Python modules. It's been around forever, so you can run it at the command line, you can hook it into your development environment. There is a timing overhead. At its worst, if you've got a really tight inner loop inside a couple of functions and you're profiling all of it, and there's lots of looping going on, maybe you get a 10x slowdown, so you have to start with a smaller data set to make sure you get a still reasonable profiling pass. But often it's not a 10x slowdown, it's some smaller factor than that. So you have to think about that a little bit, but you'll hit that pretty quickly. What's nice is you can just use a magic inside Jupyter Notebook, %LP run, and then give it a function and then some functions to profile, and it will just profile the whole thing and then dump a result. And that screenshot at the bottom comes from that. That's a part of my course where we I challenge my students and say, hey, look, we've got a couple of lines of code here. What's surprising about those lines of code? And then people will scratch their heads and go, hang on a minute, the time taken for dereferencing a couple of Python arrays is the same as the amount of time spent doing a math square root and a raised to the power 2 operation. That's kind of feels like there's different complexity involved. And it turns out when you're just using Python and hooking into the high-level interfaces, most of the time is spent on the Python high-level interface side, not the underlying math or memory references. So that's a bit of an eye-opener and a reason why we want to move towards compilation or using a tool like NumPy that gets us away from that. So line profiler, an easy win for any of you. VizTracer is a new win. It's a new win to me. It was introduced to me by one of the developers of Vaex who tweeted it at me, and I've been trying it and I begin to teach it now. You can use it in the notebook. I use it for modules. You get a statistical output file and then you visualize it in the web browser and you get this interactive diagram like we see on the right. And it records the amount of time spent in a function and the time spent in all of the functions behind it. So right at the top, that get me for indicator 1, that's my entry point that I'm timing. And then everything behind it is a whole bunch of Pandas code, Pandas and NumPy code. And all of a sudden it's laid out bare for me. I can see what's happening behind the scenes. And in this example, I've actually got a set of different queries, different ways of doing queries in Pandas. And you can see that some of them take longer time, some of them take shorter amounts of time. And then behind it, there are these different call stacks with different ways of doing a query, a mask, a group by, and pre or with or without using a categorical set. So there's different ways of doing something and it explains it and expands it all for you. Richard.
Yeah, no, I'm just curious if you, I love what this looks like. Do you have an example of using this in one of your projects where you came across something surprising?
Not in one of my projects, but I've used it to find surprising things in Pandas when I'm teaching, and then that's fallen into my project work. So I've only been using it over the last 4 or 5 months, and really I've been exploring, because I've always had the question, what is Pandas doing? Why does it take so long? And it turns out with a couple of lines of code, and then I run it through VizTracer, oh, there's the stack trace going on. If I click on any of these things, I get a code dump brought up. And so I can see what's happening in there and then begin to dig into it. I mean, here on the left-hand side, there's some dereferencing going on. I think that's a group by. In the middle, we've got the codes reference and factorization. That's making a temporary categorical for the group by. And then the math operation I want to do is the Cython in the bottom right-hand corner, the Cython operation, doing a mean or a median down there. And everything else is dressing, getting ready for that. And it's really interesting just opening this out and getting a view on the inside. So no practical use case with a client problem. That's all come from Line Profiler over the years, but I'll be introducing VizTracer when I can on one of these. So another way of thinking about profiling is not just why is it slow, but why is it using a lot of RAM? I run out of RAM. Why am I running out of RAM? And Memory Profiler is it's the granddaddy tool for this. It's been around for a long time. It's developed some slightly weird warts for profiling single lines of code. But if you just want to say, hey, I'm going to run an expression, how much RAM is used inside it, you get a magic inside Jupyter %mem, and you can do that. Or bottom left-hand corner, you can see, and you can profile each line of code in a module, just as you would with Line Profile. You get a very similar output, mainly telling you how big the process is on each line of code's execution and what the increment or decrement is on a line-by-line basis. And when you're using, say, Pandas, one of the clues for a slow bit of code can be it's doing more work than you expect. It's doing unintentional copies or an extra amount of work in the background for a reason that you don't really understand. You look into it and you realize you've got the wrong arguments going on. And so that large RAM allocation or making lots of objects can be a clue that it's going slow. And also that's why you run out of RAM and you get a memory error and you crash. And so you can go and find that in there. And I've adapted the memory profile. At the bottom right-hand corner, you can see import IPython memory usage. That's a tool that I made pre-Jupyter, back when we only had IPython, and I've been slowly updating it, which runs in Jupyter as well now. And so there in that example, you can see in Jupyter, I run a cell, df2 equals df1 times 10, and it tells me in the process of multiplying df1 by 10, we used another 760 megabytes of RAM, and in total, my process has 1.6 gigs in. So passively, as you work through your Jupyter notebook or your IPython command shell, it's telling you how long that cell took to execute, how much RAM was used during the cell's execution, and how much RAM the process is using overall. So it's like profiling in a module, but you're just getting it during your interactive development. And I find that quite useful when I'm doing exploratory work, certainly with larger data sets. I go, oh, crikey, I can see that I'm already at half my RAM. I better be careful now. Pandas is just going to run out on the next idea that I've got, and I better rethink how I'm approaching this. So audience, we're going to switch away from profiling now and think a bit about NumPy and Pandas. If you've got any tips or war stories using NumPy, I'm sure Pandas, you've got some war stories about, please do share them in the chat. Richard, do you have any observations on writing Pandas well to make it more supportable or to execute faster? You're muted, Richard. You're muted. And I was muted there whilst I tried to carry on talking. There we go.
Sorry, thanks. Yeah. No, I was saying I was thinking about this when I saw your slide deck before we started talking, and I think I'm kind of in the funny situation where I started writing Python code about a year and a half ago, and obviously, I started with Pandas and NumPy, but very quickly switched to working with Dask and with as I working at Coiled now, we do a lot of my work in Dask. So I spend a lot of time thinking about how to write Dask code well, and we'll talk more about that in a little bit. But I'm going to segue and leave this section of the tips for you, and I'm actually hoping to learn a lot from the next few slides.
Perfect. Right. So one of your high-level tips will be prefer vectorization. This is a slightly contrived example. It's the same Monte Carlo-based pi estimator, so it estimates 3.14159 using a Monte Carlo approach, throwing darts into a quarter of a dartboard and counting the number of darts that are inside the unit circle circumference and those that are outside, and the ratio of those multiplied by 4 quarters. So that's the accumulate times by 4 divided by n samples. That ratio gives you an estimate for pi. You need more samples. It's a great way when teaching high performance to burn the CPU and then show different ways of making things more performant. The problem with the left-hand example, doing this in pure Python, was a couple of problems. One is that it takes 43 seconds. So that's down, you can see the line near the bottom that says in 48, used almost no RAM, but it took 43 seconds. That using my IPython memory usage tool. So it took a long time, and that's because of all of the temporary allocations that are being incurred as it generates 100 million samples. So 100 million iterations generating an X and a Y and an X squared and a Y squared, and then updating the accumulator. Lots and lots and lots of temporaries being made. They all have a tiny cost in time to make those new allocations. On the right-hand side, with the NumPy equivalent, we make 100 million X's in one go, so one memory allocation. The algorithm has to still generate all of those random numbers, but there's one big memory allocation rather than 100 million small, slightly costly allocations. So you make the X's and the Y's, and then you do your vectorized operation. So X is raised to the power 2. Python doesn't raise each of those X's elements to the power 2. It calls to an underlying C or Fortran routine and says, hey, in the bytes in the CPU, go and raise that number to the power of 2, and then raise the next one to the power of 2. So that all happens behind the scenes in the C or Fortran layer in machine code, and then Python gets a reference back to that final result. And then the less than 1, well, that's a vectorized operation happening behind the scenes again at the C or Fortran layer, doing these operations very quickly down at the bytes level inside the CPU rather than at the high level inside interpreted Python. So you can see on in49 that the report from IPython memory usage says it used 0 megabytes of RAM for the overall execution here. It actually took 3 gigabytes to generate all of the temporaries necessary. That's the X's and the Y's, and then the temporary X's squared and the temporary Y squared. That gets you to 3 gigabytes, and then you start to lose those temporaries. So you peak up at 3 gigabytes, and then you lose everything by the end of the function. So it costs 0 RAM overall, but it peaks at 3 gig during the execution. But the execution takes 13 seconds rather than 43 seconds. So you're much better off writing vectorized solutions inside NumPy. So that's one of your tips. An even better tip is to switch to using Numba, the just-in-time compiler that's aimed at quantitative work. So it's a just-in-time compiler aimed at NumPy, only NumPy. It does some pure Python. It doesn't do Pandas. It turns out Numba is being integrated into Pandas, but it doesn't work just on Pandas. So you can't put it onto your own Pandas functions. It can do things like compile for the CPU, compile for the GPU, and even do ahead of time compilation. So you can get a binary ahead of time, which avoids the just-in-time compilation cost whenever you run your function for the first time in a new session. If you take Numba, it's kind of beautiful. You take your Monte Carlo pi on the left-hand side, the pure Python function. That's exactly the same function that I had before. And then down at the bottom, I take the njit decorator. And normally you might write &jit, so at jit around your function as a decorator. Here I'm using it as a function that calls another function. The same thing a decorator does. Njit wraps that other function. And so I say Monte Carlo pi is the wrapped njit version of the original function. And then when I invoke it, that goes to the just-in-time compiler. And because it's a purely numeric pure Python function, Numba is happy to compile it down to machine code. And then I go from 400 milliseconds, so 0.4 seconds, down to 12 milliseconds. That's what a 25, 30 times speed up, which is brilliant. And on the right-hand side, with my Monte Carlo Pi NumPy equivalent, and you might say, hey, this is kind of weird, and why is my NumPy code that you've already told me is operating down at the C and Fortran pre-compiled level? Why does that go from 27 seconds down to a faster speed? And okay, I've cheated slightly here. I've put the parallel column, which I'll explain in a second. But Numba gives you benefits on vectorized code because it can often chain together all the temporary operations. So rather than making a huge 100 million element array and then making another one and then doing a raise to the power 2 operation, raise to the power 2, it can chain the raise to the power 2 on the partial arrays that are constructed and reduce the RAM footprint that has to be allocated. And so with fewer allocations and more cache hits, fewer cache misses, less data being transferred back and forth out of the caches back to main memory, everything goes faster. So Numba can be used in your vectorized code and you'll get a speed up. That's a brilliant little improvement. And if you turn on the parallel equals true option inside the decorator, then it will parallelize the code for you across multiple cores if it can. It does it automatically. You get no control over it. There are some options in there that you lack that you might get if you use Python, but that gets a bit edge casey. Generally, you just turn on parallel equals true, and generally your code just goes a bit faster. Sometimes with 4 cores, it goes 4 times faster. And if you've got a 64-core machine, hey, maybe you get a 64 times speed up if you've got that kind of, I don't know, Monte Carlo easily parallelized approach. So Numba, super easy win if you're doing NumPy work.
Right. Yeah, just one question there, Ian, if I may.
Yeah, please.
I see that the actual estimations of the pi value change, which obviously that makes sense. We're speeding it up. Are we sacrificing anything in terms of accuracy, performance?
There's no reliability loss, because certainly in the right-hand side, we were already using NumPy with float 64s. So we already had 8-byte floats. And by compiling it, we're still operating on 8-byte floats, which have their 64 bits worth of precision. So we haven't lost any precision. We just go faster because we get more Python and memory allocations out of the way. On the left-hand side, because we're using floats again, no, we don't lose anything. If we had big int, so pure Python integers can be arbitrarily sized. They're not limited to an int64 8-byte representation. They can count to really big numbers. If we had those, it turns out Numba wouldn't compile. Numba won't compile arbitrarily large Python integers. It will only compile up to int64s. So again, we don't lose precision, but we lose a bit of functionality if you happen to be counting to enormous values. So there is a limitation there, but that is what it is. I haven't hit that limitation.
Great.
So no downside generally. So Pandas, one of the points in Pandas, so we all use it, we get frustrated, we run out of RAM, it goes a bit slow sometimes. Well, increasingly we get Numba integrated in there, which is nice. There's a whole bunch of things that are hard and a bit slow, and I cover this in the tutorial, some of it's covered in the book, there's loads of articles online. Matt Rocklin did a really nice video a couple of months ago on the new experimental arrow string data type that's inside Pandas, which lets you do faster string operations inside Pandas, because the strings are notoriously slow inside Pandas, being a NumPy object array around regular strings from pure Python. And so this new arrow beta implementation looks very nice. It's much faster. So there's lots of things that are happening in the Pandas world, but a lot of them, they're kind of out of your control. But I touched on a few bits here. So one of them is Numba is being integrated into some of the simpler functions that are computationally expensive. So the rolling window support on a time series, for example, or just any sequence of data, particularly on time series for quant work. You take your function, you've got some kind of window, and it slides along all of your elements on your very long array, repeating the same function many, many, many times. It takes a long time. Wouldn't it be nice if you can compile it? So here's one of the examples from online. Typically, you'd use Python to compile this function. So you've got your series here. I've got a rolling window, and I've got some trivial function f, which just sums up the items in the window and adds an offset. But of course, it can do something much more complex. If you apply this to all of your data using the Cython engine, then you get a certain execution speed. Cython will specialize this to some degree. This is the old way of doing it. But if you pass it into Numba, we get the number at the bottom, 100 milliseconds versus many seconds, and we get a significant speed improvement, which is really, really nice. So some of these things, these have been contributed by some of the hedge funds in our ecosystem. They make quant work easier. You may not know it's there. You just have to look for the engine parameter on some of our operations. So it's nice to know these things are in there. You just go and find the engine parameter, change it to Numba, and then hopefully your function just goes faster. That's a nice win. One way of thinking about our code is to do group bys and then do an apply. And we do an apply on some arbitrary function. It's brilliant. Here I calculate some sum and divide it by shape to get an average on a grouped thing. It's a silly example. You'd never actually do this particular example, but I've done things like this. And then gone, oh, it takes like a minute to run my group by with lots of groups on this large data set. It's kind of crazy. And then you think it back and go, actually, hang on a minute. We know that vectorized solutions give us a win. So what if instead of doing what we did before, instead we do a vectorized operation? So here, price large is a Boolean, checking if price is greater than 500,000. And then I do an aggregate on sum and an aggregate on size. So I'm counting vectorized results and I get that partial result down at the bottom. And then if I calculate it and divide it through, I get the same mean result coming out the other side. But because I'm not doing a group by and an apply, I'm doing a group by and an aggregate on a pre-computed value, and I'm timing all of that. That time operation encompasses all of that. I end up with a speed up. And if you've got lots of groups and lots of rows in each of those group bys, this vectorization approach will give you a nice big win there, which is really good. Right, Richard, yes, 50 mins, that's fine. Another tip, bottleneck and numexpra, these are optional dependencies and they need to be installed. If they're not installed, some of your code will run slower and you won't realize that. It won't tell you it's running slower. The documentation says, hey, these are optional, you should install them. You really should install them. Here's an example. If you install numexpra and we do some operation, df1 plus df2, divide by the square of them. And then that takes a couple of seconds and it peaks at 1.5 gig of RAM. If you put it through PD eval, which eval will then step behind and use numexpra as one of the older compilation technologies, all of a sudden we go from a couple of seconds down to a fraction of a second, and we don't have 1.5 gig of temporary RAM allocation. So if you're manipulating very large matrices, very large pandas data frames, you can use numexpra via the eval function, and you get a really nice speed improvement.
This is fascinating. I'm just curious, why isn't this default behavior?
So it only supports some operations, doesn't support all operations. And it's wired into eval. Eval has got it's got 2 different ways of operating. I think this probably comes back to pandas evolved in interesting ways. And so when when things settled down and then new speed ups were applied, you had these slightly weird architectural decisions. And then some of them you just have to learn. We've got this slightly difficult to use product that we have to learn some of these tricks, but some of these tricks are really worth learning because in these limited cases, you get some really nice performance improvements. It'd be nice if we had a Pandas V2 that cleaned all these things up, but it wouldn't be Pandas anymore. So we'd have to learn a new thing, which that's a bit tricky. Yeah. So, go on, Richard.
No, there's a question in the chat, but other than numexpra, what was the other tool to install?
Oh, bottleneck.
Bottleneck.
Bottleneck, yeah, put it in the chat, please. Bottleneck and numexpra. Bottleneck makes some of your math faster. You might get a 3 to 5 times speed up on some of your vectorized operations if you've got bottleneck installed. So it's really worth it some of the time. These libraries have no cost. They're tiny libraries. There's no negative to having them. They just make some of your work faster, sometimes quite a nice improvement. With PD eval, if you don't have numexpra installed and you run your operation like I've got here, you wouldn't actually see an improvement. It would run as slowly and with as much RAM as the other, the non-eval variant. And it doesn't tell you, hey, but if you install numexpra, this is bound to go faster and cost less RAM. So there's these things are a bit annoying, but once you know them, fine. It's easy to install these libraries. So I want to make sure that, Richard, you've got time for the demo because, hey, it turns out by being conversational, we've taken longer than we thought we might. So if you've got any questions in the audience, please post them into the chat so that we have a time to address them. Because, Richard, you're going to give us a little demo in just a minute. I'll be super quick here, Richard. So, Dask, why would you go to Dask? Well, you can scale up for larger than RAM situations. That's the typical thing. So it's really good for scaling pandas, but also So Dask can be used for scaling your NumPy operations and also your pure Python operations and your machine learning as well. So Dask encompasses sort of 5 or 6 different ways of scaling your analytics or engineering code. It's not just the Pandas data frame accelerator, but it is often used for Pandas acceleration, scaling to larger data sets. As soon as you've run out of RAM with Pandas, Dask is a good thing to think about. And then you start to hit some difficult edge cases because all of a sudden going to a distributed mode of thought is a bit more complicated. And I think here is where I hand over to Richard, because Richard has kindly offered to share some of the Dask onboarding questions that trump people at the beginning. And so I've gone to that a couple of times, but Richard's gone through it a load of times. So Richard, what really confuses people with getting into Dask, and what are the common solutions to get around that?
Yeah, thanks.
And if you want to give us that demo as well, then that'll be brilliant.
Sure. Yeah, I know you have a few more slides. Do you want me to just take over now, or
how about I finish off and then you can switch into your bit, and then that might be the clean way. So just for the audience's sake, so there's a couple of other libraries out there, Vaex and Polars being interesting ones. Vaex is quite mature, Polars is new, but rapidly maturing. They do a lot of the data frame things that we're used to. Vaex particularly scales to hard drive sized data sets, not in memory, but hard drive sized. Lacks time series functionality, but otherwise looks a lot like Pandas and has a bunch of libraries attached to it and is quite mature. Polars is very new. It has an arrow data types, not the NumPy data types, but the arrow data types in-memory operations with a new cleanly designed API. So taking what we've learned from Pandas and making a better API. Both super interesting technologies, definitely worth looking at, but they take you off the beaten path. So it's something to think about. And I've had some references to a couple of the talks that occurred at PyData Global recently that if you follow up on this slide, you might want to check into. And I'll give you my concluding slide, and then I can hand over to Richard, and I'll be slightly cleaner here. So my conclusions will be: reflect on what you're doing, debug, and profile. So go slower to go faster overall. I found that rather than just hammering out code, stopping, thinking about it, doing a bit of profiling, it means that I'm more productive in the big picture, and that's really where we want to get to. I've got a newsletter. It's on my blog, ianozsvald.com. That's at the bottom of these slides, and it's on one of the icons at the top. My jobs, it used to be a jobs newsletter, now it's a more general thing. I've got loads of high performance stuff in there. I've interviewed a Kaggle competition expert recently. I've got an interview with the guy who created Polars coming up. I've got a bunch of high performance stuff coming through there. So if you join the newsletter, you get a bunch of those tips and interviews. And all of my past talks are on my blog, so they're all available there. And there's a link down the bottom there, bit.ly HPP cheat sheet. That's the cheat sheet for my high performance class with a bunch of tips in there. You're welcome to download that. I'll post that link into the chat. And I think now, Richard, I'll hand over to you to give your demo and address any questions that might come up.
Sure. Yeah, so maybe actually, could you share your Dask slide? I think that's good. Is that still possible?
Yeah, just let me go back to sharing. Where did I have my Dask slides? Those ones there. That one there, or that one there?
One more. This. Yeah, great. Thanks.
That one. Yeah.
This one. Yes. Perfect. Thank you. Yeah. So I mean, I work at Coiled. For those of you who don't know, Dask is an open source Python library for distributed computing, and at Coiled, we basically offer a managed Dask service. So there's a lot of things around Dask that are really great, and then some bits that are kind of rough and difficult. And for those bits, you can come to us. Really, from my own experience, coming to grips with Pandas and Dask over the last year and a half, what really sold me on Dask and what was also the pain point, right? So Dask is, as Ian has said, resembles the Pandas API to a large extent. So the switch from having Pandas code that works, you run into an out-of-memory error where your data set is maybe not even larger than your RAM. Like Ian, I think you said you had a 10 gig data set that wasn't working on your 32 gig machine. So something you might expect to run with Pandas doesn't. It's pretty easy to switch some of that over to Dask because the API is so familiar. And I'll demo a little bit of that in a little bit. But that is also the pain point, because working in distributed is really just a totally different ballgame. And so things that because the API is similar, users often get upset when the similarity stops, right? And Pandas operation doesn't have a direct equivalent in Dask. And I found that myself too, where writing your Pandas code, and it's all, or your Dask code, sorry, and it's all the same Pandas methods that you're used to, and then suddenly one of them doesn't work. And I think, especially looking back, I really wish I'd taken the time to familiarize myself more with sort of the general logistics and challenges of working with distributed computing. So Ian, what you said about sort of going slow to go fast, like kind of building that foundational understanding. I wish I'd done more of that. I've kind of I've had to learn the hard way by just trying stuff out. But so yeah, I think there's, and I don't know if there are other Dask users in the call. Feel free to share some of the your favorite Pandas methods that you wish were easy in Dask. Those are always fun to share. And since we only have a few minutes and we talked a lot about profiling earlier in the presentation, I'd like to show off a little bit of the profiling you can do in Dask. So for that, I'm going to share my screen. Let me see if I can take this over. Oh, no, go. There. Can you see my Jupyter Lab? Yes, great. So this is a Jupyter Lab session. I've got Dask and Coiled installed in my environment here. And I've also got something called the Dask Jupyter Lab extension, which makes sort of dashboarding super easy within your Jupyter Lab window. So I've gone ahead before this session started and spun up a Coiled cluster, which is a Dask cluster, in this case of 20 workers provisioned on AWS in this case. So it's connecting to the cluster that's already running. We can go down here and using Dask API, create a synthetic time series data set. And this is familiar, if you work with Pandas, kind of calling ahead method on a data frame will give us the familiar data frame. But if you call just DDF, you'll see here that actually this is not what you would expect if you're writing Pandas code. And this is because Dask evaluates lazily. And so you specifically have to call compute. That's one of the big differences between Dask and Pandas to trigger computation on the cluster and get the results back. So I'm moving very quickly here because we don't have a whole lot of time, but there's a lot of material on the Dask docs, the Coiled docs. We give a great Dask training and also some free mini tutorials. So if you're interested to kind of dig into this more, definitely reach out and keep an eye out on our blog. The thing that I really wanted to show off is the profiling that Dask enables. So here we're doing a kind of simple value counts on our Dask data frame, actually just 1,000 of the partitions. You can see here the task graph. So this is sort of the roadmap that Dask creates to get from the data that it has to the result that you want to get. And on the screen, you saw some blips moving around as that was processing. I have another function here that will take a little bit longer, so we can dive into a few things. Just wait for that to start running. So yeah.
Richard, could I ask what bites new users the most? And I think we should run over by 5 minutes if that works for you. Sorry, listeners, if it doesn't quite work for you, really sorry about that. But we've got a lot to talk about here, and this is really interesting. I'm happy to stick around for a few minutes. So yeah, what bites new users coming into Dask, and how do they get past that?
Yeah, I mean, I think. Like I said earlier, I think one of the main pain points is running into sort of territory where it's not just a matter of copying your Pandas code, because you can get kind of a long way transferring over Pandas methods, and then sometimes you can't. Calculating a median, for example, when all of the data is distributed over a number of machines, is actually very difficult to do. And so a simple median is, as far as I know, at this moment, not supported in Dask. And that's just kind of a very small example.
So an exact median is not supported, but the approximate median, I think there's 2 or possibly 3 implementations in there.
Sure.
And so you nearly get the right answer, but it's just not guaranteed to be the sorted answer. But yeah, I've come across that with some users for sure.
Yeah. Yeah, and so I mean, one of the great things about the Dask dashboard is, for example, that you can see where on what kinds of tasks your computation has spent most of its time. So this is an aggregate time per action window where it's, your function is separated in compute, read, deserialize, transfer, and disk write. And you want this first column, the compute, to always occupy most of your time. So in this case, we're doing a good job. But these are the kinds of sort of profiling windows. You can look at worker memory, the task graph itself, to kind of get a sense of how your code is running and where you might be able to optimize things. So yeah, this is a very quick overview. I will post some links in the chat for people who are interested. There's a great YouTube by Matt Rocklin about the Dask dashboard as well. And Ian, actually, I'm curious. Do you do much work in Dask, and do you have experience using the Dask dashboard?
So I've done a couple of projects in Dask. An interesting one a couple of years ago was with there was 3 of us in different or 3 mini teams in different languages, a proprietary analysis tool, Python with Dask, and R, analyzing a data set that was on a shared machine with 64 gig of RAMs that we were all competing on. And so we partitioned the data. Each of us wrote a partition analyzer, which could analyze their partition and generate an output. And then we were verifying our outputs. And then with very simple changes to the code, I could take the Pandas 1 partition analyzer and run it on it was a CSV file, but pointed at all the CSV files, turn them into Parquet files, and generate the aggregate results, rather than having to manually point them at one CSV file, generate temporaries, and then do that, and then piece the bits together, which one of the other colleagues had to do. So it's really interesting being able to split the Pandas code, which also exposed some of the limitations where Pandas has new stuff and Dask didn't have it at the time, which now it does for those particular cases I've checked, but I'm sure there's always going to be that lag there. So some weird edge cases that came out that were a bit of a pain to debug. But again, lots of print statements, and then the graph, the task graph, and I think mainly watching the behavior of each of the worker processes and just watching it running out of RAM, and then the nanny process coming in and terminating it, and then it rerunning, thinking, all right, I've just got to partition my data down to smaller partition or more smaller partitions so that more fits in RAM, so that all the temporary bits can be aggregated together. And then it was pretty easy to diagnose once I had the mental model in place on that shared machine, and trying not to nobble my my other friendly users who were also sharing that same RAM and CPU set. But that's, it takes a little while to figure out what questions you're asking when you go from the serial Python Pandas world to the Dask distributed world, doing a Pandas-like operation. But once it works and you've got your mental model, diagnosing I found to be pretty straightforward.
Yeah, great. Yeah, so here then this is probably you've seen this kind of turn to orange, and then turn to gray, and then the worker memory profile. No.
So is this the one where they run out of RAM if they go too high, and then
if they go too high? Yeah. So
Yeah,
this is
yeah.
this is recent
go.
managed and unmanaged memory,
Yeah,
and then
yeah.
orange means it's getting up to the limit, and then it turns gray. It's writing stuff to disk, which you
And then the
really want
nanny
to avoid.
turns up and has a go at you and starts terminating things. I always get
Exactly.
amused when or nanny warnings turn up. Well, amused and then slightly annoyed because I have to go and figure something out to make the nanny go away. But it does mean the machine doesn't melt, which is always important.
Nice. Yeah. Great. Let me just have a look at the chat window and see if we have any questions. Can we get the recording? Yes.
One of the questions was the mental cost model for operations. And I'm not quite sure what that's referring to. I think this, tell me if you interpret differently, I think this is referring to, hey, how do I reason about what I expect to happen here? Because this comes up in my course. I get folk in hedge funds saying, hey, Ian, how do we reason about when Pandas is going to do a copy or not, or when it's going to modify in place or not? Actually, it's really hard because a bunch of the time copy is true or copy is false in the argument, and sometimes copy is none, in which case there are arguments inside the function where it will or won't do a copy dependent on some other options. It's really hard to reason about it. So Pandas makes that complicated, and Dask will compound that because it has to respect what Pandas is doing because it uses Pandas internally. So yeah, do you have any observations on reasoning about how some parts of the workflow in the Dask side will operate in terms of memory used or time taken?
Yeah, I mean, I think it's so hard to say things kind of blanket statement for all workplaces.
Yeah, sure.
We really see working with clients in different fields is that I think, and you pointed to this too, right? With whether you're working purely in NumPy or if you're yeah, because maybe that's an important thing to state. Dask doesn't only parallelize Pandas code. It often is seen as such, but it parallelizes NumPy code just as well. So it's, yeah, I'm not sure I have kind of a blanket answer there. I do think there's a great blog which I'll share by one of the Dask maintainers about tackling unmanaged memory in Dask, which I found, which has some really good sort of practical tips on things to do or avoid when you see your Dask dashboard kind of turning orange. So I've shared that in the chat. Some really practical
examples. Chat's going to disappear as soon as we close the session in just a minute or two, which is, so if anyone wants to grab that link, go and click on that link now and open it up, and Christiana will bundle this all together for us. And I'm sure Christiana is watching the chat because, yeah, as soon as we close the Zoom window, Zoom loses the history, which is really annoying with the chat stuff. So if you want to grab anything out of chat, please, everyone, go and grab things out of there. Just opening that link
and
up now.
I see some other great questions, and I'm not sure we're going to have time to address all of them. So I'm also going to share a link to the Dask Slack, as well as to the Dask discourse. So those two are in there. Those are two great places to ask more of these questions. So you can ask questions there, and help you out. And if people are interested in learning more about Coiled specifically, I will also share a link to the Coiled Slack, where you will find me and other people to answer your questions and continue this conversation, because there's a lot more to be said.
Absolutely. This was just a preview, a teaser for all of the amazing stuff out there. So yes, as Ian and Richard just said, I will be sending out a big email with links galore to resources from Ian's website, his newsletter, which is amazing, Coiled resources. And I think Richard brought up, we do have a free live Dask training coming up on December 9th. So if I see some people in the chat saying they're excited to dig into Dask, that's a really good way to get started. And I will of course send out a recording of the conversation we just got to participate in. so that everybody can go back. And I believe actually the chat is recorded too. So you'll be able to.
Oh, really? I've always lost it whenever I've tried recording. So if there's a magic button for that, I'd love to know what the button is.
Well, in the special follow-up email to you,
okay.
I will include that.
Yeah, absolutely. Right, please. And I would certainly, for the rest of your audience, if you're learning Dask, I would recommend you join that free training. Dask, it's a bit like Pandas. You do your first 5 statements and you're like, way, I'm off to the races. This is brilliant. And then you hit something and you stop. And then all of a sudden you flatline your learning curve and then you bash your head and you go to Stack Overflow and then you make a step up and then you're off again. And Dask can be similar. Some things are really easy to get going with, and then you do something and suddenly the distributive model bites you and then you get confused. If you join that training and then work that through and bring some of your examples, you'll be much smoother on your onboarding.
Absolutely. Yes. And that's led by Natty, who's an OSS engineer over here at Coiled, and she'll get you started for sure. But Ian and Richard, thank you so much. That was a fantastic session. And to the participants still here, thank you for being active in the chat. That was awesome. And yeah, thank you both so much.
Thank you for supporting the chat, and thank you for indulging us in overrunning. Sorry everyone for overrunning, but yeah, there was just it was a lot to dig into there, and that was good fun. So thank you very much, and thank you for all the participation in the chat. That's much appreciated.
Yeah,
totally.
Sure. Great to see some stories and some good questions. So hope to see some of you in either the Dask or the Coiled Slack, and continue the conversation. Ian, thanks a lot for your time and your insights.
Thank you very much.
Appreciated. And,
absolutely. All right. Thanks so much to all.
Right.
Have a
Cheers,
great
everyone.
rest of your day.
All right.
Bye-bye.
Bye.
Bye-bye.